Well, hello. In this video, continuing in my series on teaching psychological statistics, I'm going to talk about performing an independent samples or independent measures t-test. In my previous video, I talked about performing a one sample t-test, and this one's going to be a little different. And as I emphasized in the previous video, one important aspect of learning statistics is that you have to not just know the steps for doing a particular test, but you have to know in which situation should you be using that test. You don't want to use the wrong test with inappropriate data that it's not designed for. And so when should you use an independent samples t-test? Well, it's kind of in the name, but let's talk about what that name means. You should only be using an independent samples t-test when you have exactly two groups of data for comparison. Specifically, you have two independent samples, two samples, so we're not dealing with population data, and these two groups of scores, numbers, observations, whatever you got there, they are not from the same participants. They're not tested twice. It's not a before and after type of situation. This is where you have separate scores from separate subjects or participants, and they don't influence each other in any way. So they shouldn't be like tested at the same time, looking at each other's answers, being influenced by each other's performance. They should be separate scores, independent scores. And you only can do this with two groups. If you have more than two, you have to do a different type of analysis that I hope to make a video in the future about called analysis of variance. Okay, so in my previous video about the one sample t-test, the dependent variable that we used was ACT scores, or were ACT scores. So in this case, I figured let's just continue that. We're still using ACT scores, but now we have two independent samples, independent groups of ACT scores. These sample sizes are still too small for most actual research studies in the real world, but hey, we want to have few calculations because our purpose here is just to demonstrate the steps. In the real world, you'd have much more data. If you were doing it by hand, it would take you much longer. All right, so just like before, I have labeled one group X, right? These scores, these X's, that's one group of participants. I labeled this group Y. All right, so that's arbitrary. I made that up on my own. You can call them whatever you want. I decided to go with X and Y because that's how I like to do it. Now, what are these? What is this supposed to represent? And this is made up data, completely made it up, all right? But these are ACT scores, and this group is like your control group or comparison group. These folks did not get any kind of ACT prep whatsoever. They just said, here, go and take the ACT. This group over here, they enrolled in a specific course meant to help them do well on the ACT, an ACT prep course. And so we want to see, is there a statistically significant difference between these two groups? In particular, what are we going to compare? Just like with other t-tests, our goal is to compare the means. In this case, we want to compare one sample mean to another sample mean. Previously, we had some standard score, some single score to compare to. This time, we have to compute both of our scores that we're going to be comparing. We have to compute a sample mean for each sample. All right, so for group one here, all right, our control group, our X group, and for our experimental group, the intervention group, the folks who had the ACT prep, that's going to be our Y. So first we have to compute means. I know you remember how to compute means, right? But I'm going to go ahead and do it. I'm sure you can get this on your own if you've been taking statistics. But just to let you know, in case you don't know how I got these numbers, this sample mean, and there are different ways you could do the abbreviation, the notation. I have, first of all, and we're going to need our N for later, the sample size. And so I put N sub X. You could also do N sub 1 and just arbitrarily say, hey, this is group 1. Whatever labeling works for you, but you are going to have to keep straight which numbers go with which group. So I have N sub X equals 4. How do we get that? 1, 2, 3, 4. All right. What you do is you add these numbers up and you divide them by n. So I added these numbers up, divided by 4, I got 20.5. The n for y, that's a y there, I know it doesn't look like it. The n for y is also 4. You add these numbers up and divide by 4, and you get 25.25. Now, it's awfully tempting to look at that and say, they're different. They're different, we're done. They're different. They're different, this one's better. They benefited from being in the ACT prep program, I'm done. If we want to do things with statistics, and that's how we're supposed to be doing it in a scientific field, and yes, psychology is a science. That's why psychology majors have to take all those science classes and statistics classes. All right, we can't just look at that and eyeball it and say, looks different. We do something a little bit more precise than that. So we're going to perform a t-test to see if they are statistically significantly different. If you don't know what that term means, I'm hoping to make a separate video about that, but we are roughly seeing if we have a low probability difference between the two. We want to see that our difference is larger than you would get just from sampling error. If you don't know what that is, I think I covered that in a previous video. That's something that should be covered fairly early in a statistics class. All right, so how do we do our t-test? All right, this is our formula for the independent samples t-test. Now, I've got it kind of crowded over here because it's almost like I'm leaving room for things I know I'm going to have to compute. But what we have here is t equals sample mean 1. I could have put x. I put 1 here because that's how it's written in the textbook. So it could be x. All right, so mean 1 or mean x minus sample mean 2, the mean for y, minus, what's this over here? These are our population means. We don't have access to the actual population that these samples are drawn from. But that's part of the formula. How are we going to do this if we don't know what our population parameters are? The good news is that the null hypothesis, I'm definitely going to have to do a video where I explain about null hypothesis, but the null hypothesis for this test is that population mean 1 minus population mean 2 equals 0 because they're equal. If there's truly no difference, no effect, when you subtract the two means, they should equal 0. So the good news is this is 0. So really, it's really sample mean 1 minus sample mean 2 over, oh, what the heck is this? This is another estimated standard error, similar to what we had to compute in the one sample t-test, but there are more individual steps because you've got 2 sets of data to deal with. Just like with the independent samples t-test, the longest part is getting this denominator. I mean, the numerator is easy. Mean 1 minus mean 2. Okay, 20.5 minus 25.5. I can compute that. All right, but we need that. Where do we start? Well, we are going to need to compute something called pooled variance, which requires us to commit statistics, to compute the sum of squared deviation scores for each of these. Previously, we had 1 sum of squares score to compute. Now we have 2. We have 2 separate of everything in this pretty much. So let's get things started for that. All right, giving you a nice view of the board here. All right, so we have our x, we have our y. For each score, we had to compute something called a deviation score. And so here's a deviation score. The deviation score is the score minus the mean. We have the mean down here. So 21 minus 20.5 gives you 0.5. Then you have to square each deviation score. So 0.5 squared is 0.25. So I did that with all of these. Compute a deviation score, square that deviation score. And the way we get the sum of squared deviation score is you add these up. So you add these numbers up. The sum of squared deviation score for x is 13. You do all the same things for y. You compute a deviation score, square it, and then you add up, you sum all the deviation scores. The sum of squared deviation score for y is 10.74. So what do we do with that? We're going to need that to compute our pooled variance. All right, time has passed. I don't know if you can tell, but the sun has gone down. And so since the lighting was not so great on the board here, I do have an extra light source. It's going to reflect off my glasses, but I'm sure you'll be okay. You're not looking at me anyway. You're looking over here trying to figure out what we're doing with all these numbers. So we have our sum of squared deviation scores. What are we going to do with them? We have to compute pooled variance. All right, so I'm using my pen as a microphone. So I have written the formula for pooled variance here. Now, we used variance previously with a one sample t-test, and we only had one sample then, one variance. Now, we have two sets of data and two sum of square scores, but we're only going to compute one variance. We're going to compute a pooled variance for the whole study, essentially. And so we're going to use this formula. It still has the abbreviation S squared, but it's got this little p because it's a pooled variance. And we have sum of squares 1, which I could put sum of squares x plus sum of squares 2 or y over, now here's degrees of freedom. Now I talked about this in my one sample t-test video. If you don't know what degrees of freedom is, just for practical purposes, you compute that as n minus 1 for each group, for each sample. So n minus 1 and n minus 1, and they both happen to have the same sample size here. All right, so right here we've got 4, n minus 1. Oops, that's going to write kind of wiggly. I'm writing DF for degrees of freedom. Okay, yeah, it's really writing well. What's 4 minus 1? We know this. It's 3. So degrees of freedom is 3 for each one of these. I'll go ahead and write this in the same color. Let's see, I'll write that here. So degrees of 3. Multitasking is difficult. Degrees of freedom are 3 for each one. So we're going to have 13 plus 10.74 is our numerator, and then we're going to have 3 plus 3 as our denominator. All right, here look, we have a convenient glare right over the pooled variance. All right, gotta love it when that happens. That's what happens when you're high tech. So when we compute our pooled variance, 23.74 divided by 6, and we got these numbers because we added these numbers, divided by the 2 degrees of freedom added together, we get 3.96. Now, I did round to 2 decimal places. I do allow my students to round, and I say if you're going to round to 2 decimal places. If you have another instructor for another class, they may have other policies about rounding. Always make sure you do whatever they're expecting you to do. And so that is our pooled variance. But that's not that. We still need to compute our estimated standard error. All right, so we've got some more computations to do. Isn't this fun? A lot of students are like, no. Okay, yeah, but we have to get to the point of having a t-statistic to interpret. So we're almost there. We're getting there. All right, so now we have our denominator. So this is the formula. The formula for your standard error, your estimated standard error when you're doing an independent samples t-test, the formula is the square root of the pooled variance over the n for the first group plus the pooled variance over the n for the second group. Now, pooled variance is just one number. You use the same pooled variance no matter what. But in a situation where the n's are not the same, you might have unequal sample sizes. You do have to pay attention to your n's. You might have different n's being inserted into this formula. So in this case, they both have an n of 4. Now, I'm going to warn you, one mistake my students often make, or they just kind of get tripped up and confused and they have to check themselves and they erase a bunch of stuff. Remember that sometimes you're using n minus 1, like degrees of freedom is n minus 1. Other times you're using n. And so I tell my students, I let my students have the equivalent of a formula sheet. I'm like, make notes, make notes and make sure you keep it straight. I don't know what you are allowed to have for your classes, but one thing that often is confused, in addition to forgetting all the steps, is getting confused about when you use n and when you use n minus 1. So what we do is when we plug in our numbers, so we have 3.96, we got that there as our pooled variance. divided by 4, which is our n, and it's the same number for each one. In this case, it isn't always. You're going to get 1.98, and then you take your square root and you get 1.41. So now we finally have all the pieces to fill in this formula. Remember, this is 0. The population means 0. Mean 1 minus mean 2. We're just going to take this number, subtract this number, and we're going to divide by this number. Are you ready? We're going to get our t-statistic. We now have a t-statistic. So we plug our numbers into the formula. So we have, I erased some stuff and rewrote the means here because we do need those. They are important. So 20.5, that's the mean for group 1, or as X as I called it earlier, minus 25.25, the mean for group 2, minus 0. Remember, 0 because the null hypothesis says that those population means are not different. If that makes no sense to you, it's okay. It's negative 0, minus 0. So really, it's really just subtract mean 1 from mean 2. Think of it that way if that helps you. Divided by that estimated standard error, you get negative 4.75 divided by 1.41, which is negative 3.37. So I put a little frame around it. There's our t. Yay, we're done. Almost. We know what our t-statistic is. Now we have to ask ourselves, is it big enough to be statistically significant? A t of 0 means there's no difference, no effect. Well, it's not 0. Is it far enough from 0 to be statistically significant? So you may know or remember or need to be reminded or need to be told for the first time that to know if this is a statistically significant t-statistic, we have to look it up in a t-distribution table. Now, before we do that, we need to know some things like, let's see, what would be a good color to use? I'll pick blue. Blue's nice. It's nice and dark. All right. So when we look things up in the distribution table, the t-distribution table, we have to know, first of all, we need to know if we're doing a one-tailed test or a two-tailed test. Did we specify whether one group was going to be higher or lower, or did we just say they would be different? I didn't say that at first. It would be reasonable to say, hey, if they're taking a special ACT course, they should probably have higher ACT scores. So let's say that that was the hypothesis we were trying to support. We were trying to investigate the hypothesis that participants enrolled in an ACT prep course would have higher ACT scores than those who didn't take one. All right, makes sense? Since we're specifying the direction of the effect, the direction of the difference, then that would be a one-tailed or directional test. So, put that right here. We have one-tailed. Ooh, that's hard to write on that part. It's a one-tailed test. We also need to know our alpha. I'm going to try to write the little alpha symbol, the little Greek symbol, lowercase alpha, if you want to call it that. Alpha, or you could write the word alpha. Alpha equals what? Usually, well, commonly, not always, but commonly we use alpha set to 0.05, meaning approximately 5% chance, or you want a less than 5% chance of making a type 1 error. What the heck is a type 1 error? That's the risk of saying you have an effect when you really don't have an effect. All right. I am simplifying. So you need to know your alpha level to look up your critical value in the table. So we're going to use the standard. We're going to use the very commonly used 0.05, 5% risk. What else do we need to know? We need to know our degrees of freedom. Now, earlier we computed 2 degrees of freedom, but we need the degrees of freedom for the whole study. So the degrees of freedom for the whole study is going to be n-1 plus n-1. Each group had 4. So that was n equals 4 for each group. So n-1 is 3. So it's going to be 3 plus 3. So it's going to be 6. 6 is going to be your degrees of freedom for the whole study. So I'm writing df equals 6. All right. We're ready to look things up in our table. Now, because of my low tech here, I'm just going to have to, I'm going to have to impose a picture of the table that I'm using as a sticker in editing, and hopefully it will be evident what I'm looking for. If you don't know what I'm talking about, most statistics textbooks are going to have this thing called the t-distribution table in the back of the book, often in an appendix. It's going to be somewhere in the book, or your statistics instructor should give you a table, like maybe a sheet of paper, PDF file, or something like that. And you can also find them online. My favorite one to use, I just get online from the website Scribbr. Scribbr. You can just download, I think it's a PDF file, but in my opinion, it's organized well and easy to use. But you can use, they all have the same info, it's just organized differently or might have different visuals. All right, so we got to look up our values in the table, and I dropped my clicker. Now, previously, we were doing, in the one sample t-test video, we were doing a two-tailed test. So we looked in the table that said two-tailed tests. It is very important that you look in the correct table or the correct section of the table, because sometimes they combine the two tables into one. You have to make sure you're looking under one-tailed test. All right, so looking under one-tailed test with alpha set to 0.05 and a degrees of freedom of 6. And so I look in my table, I find degrees of freedom in the first column, and I find 6, and I go over to the column for alpha set to 0.05, and I see that the critical value, let's see, got to find a good spot to put it. I'll put it right here, just because we need a space to put it. CV, critical value, equals 1.943. All right, do you remember what that critical value means? That's your minimum. That's the minimum t-statistic, and you ignore the sign. All right, so you where is our t-statistic? Right? Cover up the sign. All right, another way you can think of it, it has to be far enough away from 0. So you cover up the sign, this number here, it has to be higher than 1.943 to be considered statistically significant. Is 3.37 higher than 1.943? You know this. You know this. Yes, it is. All right. So in this case, we do have a statistically significant result. We can reject the null hypothesis. If you don't know that terminology, it should be covered in your class. I'm hoping to cover it in another video. Right now, we're just talking about all the steps, but in research, it's often a good thing to reject the null hypothesis. You haven't proven your proposed research hypothesis, but it's good when you can reject the null hypothesis. The null hypothesis says there's no effect. It's good to reject the idea that there's no effect if you think there is an effect. So our results are consistent with there being an effect. They don't prove it, all right? But they're supportive of that. So how would we write this in APA format? All right, so our result. Writing up our result in APA format. T, lowercase t, italicized if you're typing a paper in APA format. And now you don't just write T equals your number. You write T and then put your degrees of freedom for the whole study in parentheses. So T with 6 in parentheses, because that's n minus 1 plus n minus 1. That's how you get that number. Equals negative 3.37. And here's the important part that tells you whether it's statistically significant. P, lowercase p, is less than 0.05. Is that a good thing? Yes. We are often very happy. It depends on what idea you're specifically testing, but most of the time we are setting up our study so that we want to find that P is less than 0.05. That means you have a statistically significant result. That means that this result is unlikely. It's unlikely, this difference between the two groups is unlikely to be from just sampling error alone. We're hoping it's from our independent variable, the intervention, the treatment that we're testing, the ACT prep. We're hoping the fact that our groups are different because they are different in whether or not they had ACT prep or not. All right, so you would say this is a statistically significant result. All right. If it had said greater than, that would mean non-significant. We have to keep the null hypothesis saying there is no effect. All right. So that's how you'd write it. So that's the step-by-step of performing an independent samples t-test. Now, I have not gone over effect size. Nowadays in research, it's pretty standard that you would also include an indicator of effect size, but I'm going to go over effect size separately eventually. All right, and good luck with whatever you're working on that brought you to this video.